Hey everyone, and welcome to the SimScale webinar. Today we have a very special guest, and I'm really excited to present to you how Rimac Automobili leverages SimScale for faster product development. I'm your host and moderator for today's session, Youssef Murad, and I'm a product marketing engineer here at SimScale. It's really a pleasure and honor to host this webinar today, most importantly because I have two experts in electronics cooling on my side today. The first speaker of today's session is my great colleague from SimScale, Alexander Fischer. With a background in computational mechanics and control technology, Alex Fischer worked for 10 years in different product and engineering roles, building a fully cloud and web-based solution platform. He is a co-founder of SimScale and leads the company's efforts for thermal management and electronic solutions. I'm also very excited to welcome our second speaker for today, namely Antonio Radonic. Antonio is a battery system engineer at Rimac Automobili, where he is responsible for the design, development, and validation of high-voltage automotive battery systems. At the end of this webinar, we will have some time to cover all your questions in a dedicated 15-minute Q&A session. So if you have any questions about the webinar, today's case study, Rimac, or SimScale in general, please put them in the chat or little Q&A box, and we will make sure to take them one by one at the end. So let me briefly introduce SimScale. So we see many engineers and designers new to SimScale who are curious to learn what we are actually all about. So let me briefly introduce SimScale to those who are not familiar with our platform yet. We are committed to making engineering simulation more accessible, from thermal, structural, and fluid simulations to other industries who couldn't afford simulation so far. And we strive to introduce digital prototyping into any R&D cycle. This means that we adopt digital prototyping, which also means that we can explore the full design space with a desired accuracy and also reduce trial and error that comes with physical prototyping. So to sum this up, we are focused on delivering computational resources that scale up on demand. We offer a streamlined simulation workflow and offer modern sharing and collaboration features. And we would like for engineers and designers to be able to simulate early, simulate more, and especially simulate now. Or to put it even more crisp, you come with your CAD model and leave with a design decision. So let me quickly also introduce Rimac Automobili today. And as Martin Rimac, founder and CEO of Rimac Automobili, puts it, it all began with one man and his dream in a garage. Rimac Automobili was founded in 2009 from a love for automotive and with a vision to create high-performance cars for the electric era. Today, they are around 1,100 people strong technology powerhouse focused on designing, engineering, and producing electric hypercars and high-performance EV components for the global automotive industry. And of course, a lot of you are joining us today here to share the passion for hypercars especially, and you are also automotive enthusiasts. You might have heard of Rimac's latest hypercar, the Nevada, and like the mighty Storm system from which it takes its name, Nevada is a force like no other. Designed, engineered, and handcrafted in Croatia, defined by function and forged from a love for automotive, Nevada was born to outperform. To create such an engineering masterpiece, Rimac and their technology powerhouse, segmented into different services, works hard to make this hypercar dream come true. And what makes this webinar really, really exciting is that engineers from different services basically work on this hypercar. And I'm very, very excited to have Antonio together on this webinar, together with my colleague Alexander, building basically the powerhouse for today's webinar to make sure, also make sure to take this opportunity to ask all of your questions during this webinar. And of course, we will cover the service, namely battery packs, in today's session. Let us quickly have a look at today's agenda. Today, we will be demonstrating the benefits of engineering simulation in the cloud and Rimac Automobili and how they are accelerating their product development in different stages and areas using cloud-native simulation. The case study today will be liquid-cooled battery module. And as announced at the beginning, we will have 15 minutes at the end for everyone to ask questions. So let us quickly talk about design at Rimac Automobili and how to design hypercars and empower designers by using simulation. And the first question is going out to our guest speaker, Antonio. Antonio, how did Rimac Automobili start using SimScale, especially in the battery system team?
Hello, Youssef, and hello to all of our viewers today. And that's a very good question. How did we start using SimScale at Rimac? In the battery system engineering department, the department I'm part of, we noticed there is an opportunity to integrate simulation activities into the design activities which we are doing. And in order to evaluate all the available simulation options which are available on the market, we started an extensive benchmarking process, which included a review of several options. During this benchmarking, we contacted you as SimScale, and we set up to perform several trial simulation cases where we wanted to see what were the capabilities and opportunities in which we can leverage SimScale into our design process. And in the end, after we tested several solutions, we selected SimScale as go-to option.
Very, very interesting. And I think also Alex and you will later on speak a little bit about how you actually deployed SimScale at Rimac. So that's very, very interesting. Thanks, Antonio, for the insight here. With that, I'll now hand over to my colleague, Alexander Fischer, who will talk about harnessing the power of the cloud. Alex, the stage is yours.
Yeah, thank you, Josef, and also welcome from my side. I want to give you some insights essentially on what Antonio just mentioned, right? So some of the questions we have for him, also highlighting what this means for SimScale, how we really deploy our platform, and potentially also outside of Rimac's use case, what you can expect essentially if you're working with the platform. So we asked how Rimac started, right? The start on SimScale is centered around what Josef mentioned in the beginning. We are really centered around accessibility at SimScale. We want you to simulate early, more, and now, and we need to give you the chance to simulate, right? So what you see here, bring a CAD model, leave with a design decision, also that counts essentially for your starting experience before you might even go with SimScale or buy SimScale. To make use of simulation, obviously you need to have the access, and that's also kind of our DNA, that we see that simulation has such a great impact on many design decisions, on many design cycles inside of organizations. We just see that it's not used to the extent that it would be valuable, and we really want to make this happen essentially, that everybody who could get some value out of simulation can access this and use this. And to do so, essentially, we're trying to kind of overcome some barriers. And that is, for example, that in many cases, simply the hardware resources that are needed to simulate something, it's often very hardware intense, are not available to you, right? Or you need to go with some decision, some trade-off between what do I provide as software licenses and hardware resources to my team to always have the chance to simulate and design faster, but at the same time, all of these licenses and hardware resources cost you money, and you need to find essentially a trade-off. We don't want you to make this trade-off. We want you to simulate at the moment where you need simulation, and if you don't need it, then this is also fine. But really make use of it when it's required. This accessibility is obviously driven by this cloud-native platform. So it's always available. It's not just always available for you at work. You can also obviously use it if you're in a remote setup. You can use it with any internet connection device that you need, and also different ones. And it comes without saying, obviously, that while you are simulating, while these simulations run in the cloud, you can operate on your computer, on your device as usual. So you don't need to kind of leave it at the side and then come back when the simulation is done. You can continue your design process, set up the new geometry model for the next design iteration, or start a new simulation at the same time. We also see that many people do not use simulation simply because they are new to it. They don't know the ins and outs. They have some knowledge missing to do this. And our approach to kind of bridge that gap is having in-product support. So you can just pop up a chat inside of our product, get in a conversation with one of our support engineers, or even call them and talk with them. So there is no need to file some ticket in some support service and weeks later get a notification that it was now closed or resolved. You get direct support, and specifically when you start using simulation, this is extremely important and helpful when you start using SimScale, of course. And we try to build our product that it's both for the expert, but also for the beginner, for people new or adjacent to simulation, so that it's easy to set up, that also the experts can help you by, for example, templates. We will also raise this later on. And this whole kind of ecosystem of making a simulation platform accessible you will also experience when you get started with SimScale, be it with a user test, just trying out our platform with full resources, or be this a demo project that you do with our support, making more use of this proactive support already when starting with simulation.
Excellent. Thank you so much for the insights, Alex. I think I have also now a follow-up question for Antonio, and then a very interesting one for Alex as well. How is cloud native simulation actually implemented at Rimac today? Because, Antonio, we have seen that you have several services that you offer. For example, one of them is the big battery pack team. How did you deploy SimScale inside of Rimac?
So currently inside Rimac, SimScale is used by several departments which are designing components for various parts of the battery pack, as well as for other components. And SimScale is used mostly by design engineers who use it as an additional tool which is available to them and which enables them to explore multiple design options than it was previously possible. However, additionally, inside the division, Rimac Automobili possesses also internal CIA department, which is performing simulations in parallel to design engineers. However, these simulations are performed on models which are higher level and which are much more complex than the ones the design engineers perform.
Very interesting. And Alex, maybe you can clarify here if this is like a typical use case for SimScale customers, or if you have any other use cases, how SimScale can be deployed inside of an organization.
Yeah, so we see this as a typical use case, and also one we really want to kind of work with our customers with to make as easy and also as collaborative within the team as possible. But we also see other use cases for SimScale where companies really just start using simulation, so where there is no simulation implemented at all. Some companies obviously then incorporate simulation also as a complementary tool, as we just heard it from Antonio. But to kind of state it as in a very simple way, if there is a designer or any engineer in your organization that should be using simulation and is not, then SimScale likely is a use case for you. We also can show this maybe in a bit more detail. So what we think simply what traditional CAE, which delivers a lot of value when used right, is not yet capable of doing, is really getting the simulation value out to all people that can use it. And we wanted to kind of make this a bit, via this visual, highlight this, that usually in an organization you will have a design team and you will have an analyst, right, that does the simulations. And you see already in green that this analyst will have accurate results. He will likely have the hardware resources and software licenses that he needs to do the simulations. But you see within the design team that there will be multiple problems. So first of all, obviously, there will be designers that have no simulation access at all. There will be also some designers that might have, but they don't have the hardware essentially to run simulations, or at least run simulations and at the same time continue with their main job, right, which is designing, optimizing the design that they want to work with. And there will be some designers that will just struggle to get accurate results or results at all because of the setup that they do, how they incorporate the physics. All of this is obviously a struggle. And in our perspective, traditional CAE is not really delivering on what it promises here. You will have problems with the efficiency around this, suboptimal designs by doing not enough simulations or too late. And based on this, overall get a too low ROI on what you're doing here. So we really want to change this around, make it accessible to people, but also make sure that it really provides the value that it has. And how we're doing this is essentially that we see SimScale as a platform where we connect the designers and the analysts all around this platform, allow real collaboration, meaning that every designer has access, but also that the analyst has the chance via simulation templates to share his knowledge, to ensure that the quality is high of what is done, help the designers to really work, but also be maybe just the partner who validates if the simulation in the end is the right thing or what was done correctly. As in the end, the only thing you need to kind of join this network of simulating engineers and analysts is really just one device that allows you to log onto your account and start simulating. Yeah, and maybe to give some kind of more details on what this platform then means in the different areas of application. So we already talked a bit about collaboration and enterprise. So the analyst, by the way, can also have the chance essentially to highlight some facts. He can enable certain features for users or not. So you can obviously control these, but the collaboration part is certainly the strongest. This is also the way how we do our support inside of the tool, so that we become essentially a support team member inside of your organization by helping your engineers simulate. Secondly, we have instant access and workflow integration. So SimScale is built very easy to connect into your workflows. We have an open API. Josef will also mention this later in the presentation. We try to build it very easy, accessible, all via the web browser. So it's very easy to start with, and it's also easy to use by all of your designers and team members. The third point is that we are built on proven simulation technology that is out there for years. If it's the simulation technology that we built or the simulation technology of our partners that we are integrated into SimScale, there's very different application use cases. We will also see a bit more about the physics, and all of this is validated and proven simulation technology. And at last, what I already mentioned, the HPC computing and data management, which is all based on the cloud, and you just access via a laptop. So via this, we really want to kind of overcome these hurdles that I mentioned beforehand, right? So that you can use this platform as a team to make product innovation faster, to have lower costs and make it economically feasible, and via then extend really the simulation use inside of your organization, make decisions earlier, make them faster, and also be faster in your design cycle.
Great, Alex. Thank you so much for the insights. I think what also would be interesting to a lot of the people in the audience today is which types of physics are you actually covering using SimScale at Rimac? Antonio, maybe you can give us a little bit of insights there.
So we are trying to use as much as possible of what SimScale has to offer us. So first, maybe regarding the thermal management of the battery pack. Here we are using it quite frequently to investigate what kind of flow we can expect through various geometries of cooling plates, pipes, etc. What kind of pressure drop values we can expect on these geometries as well. And furthermore, we like to explore what is the heat transfer. So we are performing thermal simulations to see what kind of thermal gradients and what kind of heat transfer we can expect on various concepts and various designs. On the second topic for which we are using it, we like to investigate also the structural integrity of our designs. So we like to see what kind of loads and what kind of stresses we expect in our structures, as well as in the cooling elements. We like to explore what kind of pressure, what kind of loads we can expect with the applied pressure inside of various geometries.
Mm-hmm. Very, very interesting. I think a follow-up question then for you, Alex, would be, is there maybe more to it than only thermal management? I mean, Antonio talked about various use cases here, but maybe there's more to it. Do you have, maybe you can add your 2 cents right there.
Yes, absolutely. So in electronics, we mainly see obviously the thermal use case. It's really the center of all design, but there's other parts to it as well. Obviously, for electric vehicles, the safety around the battery pack plays a big role. There are other maybe smaller questions around snap fit analysis, where you want to run a detailed analysis on how the plastic essentially deforms if there might be failure because of that. We also see that sometimes when you're trying to optimize a flow channel, you're really trying to get into the details of where the pressure drop is essentially caused, and you're not even that interested at that moment about the thermal aspect of it. So you might only want to run a CFD analysis. So kind of these different thermal CFD and FEA analysis are possible, and obviously we want to really get the designers to use maybe even different physics per designer that he can look into the specifics of this. And I guess you can also give us a bit more of a detailed overview of which physics we really cover at SimScale, also outside of electronics.
Okay, let us have a look at the theoretical aspects of cloud computing and maybe compare them to traditional CAE tools. And for that, you can see the slide that Alex pulled up. Let me quickly spend a couple of minutes to talk about how simulation will be used and deployed in the future. Here you can see a conceptual breakdown of the product lifecycle going from the conceptual phase on the very left over to the manufacturing and production phase on the right side. And most simulation processes or designs are working like that, which we can see right here, which is admittedly a very simplistic way to look at it, but captures the status quo of most workflows quite accurately. Typically, you have on-premise hardware rolled out on an elaborate software and IT stack, which costs you not only a fortune, but also requires orchestration between different teams like engineers, IT support, and so on, and potentially other vendors to support you in your simulation journey. And that's relatively complex in my opinion. Note that this is on purpose, but at the stage of the design cycle, because it's actually like that in real life, we can say, but very simplistically demonstrated. And also, as you can see, when we look at the design and engineering stage, this design validation stage is usually very late in the R&D process. So we can say when there's a mature CAD geometry, then I'm using simulation. It's like an if-then scenario. So once you have the mature CAD geometry, then you are thinking about using simulation. But now there's a lot more to that, right? So today there's a lot more movement going from reactive design, as you can see on the right-hand side, talking about design validation, actually going towards iterative design, so simulation actually driving the design process. There's also a lot of other things such as generative engineering in the early stages up to predictive maintenance and leveraging things like digital twins on the production side of things. So how is SimScale approaching this? All the IT complexity is taken by SimScale and handled by us. Whether it is data storage or node handling, all the various bits and pieces you don't want to deal with, especially as an engineer, so there are absolutely no worries for the end user. On top of that, we have integrated a lot of neat technology modules that are tightly integrated into the SimScale ecosystem, such as CAD editing, meshing, and a lot of other capabilities, which you can see right there. Also, now that Alex mentioned the physics, these applications range from structural mechanics use cases, thermal, and also CFD capabilities, which you can see right here. And everything is packed into one single SaaS application, namely SimScale, which gives you access to all of these analysis types. Also, everything is accessible. So SimScale is accessible via a graphical user interface, short GUI, and also accessible programmatically via an API using C# or Python. And all SDKs are available on GitHub. This is not all by us. There are a lot of third parties involved and also a few that leverage our API. And if you're interested in that, we are more than happy to share a few more customer success stories with you. And a follow-up question to Antonio. Antonio, how would you personally describe the main value you gained from using SimScale at Rimac Automobili?
Well, to answer this question, I would like to highlight maybe the three main points which we consider are the main values. However, there are probably many more. So for the first point, the design engineers expand the knowledge about the simulation world. Also, SimScale here is very helpful because we have lots of tutorials available to us, and also the customer support is great, and they are always able to troubleshoot our problems and to support us. For the second point, which is maybe most valuable to us, is that we are able to accelerate and enhance our design and development process. Here, timing is usually crucial to us, and SimScale enables us to reduce that time gap and to accelerate our design process. And for the third point, the design engineers can expand on their knowledge about how does some design change impact the design overall, and what is the physical behavior of our products. So here they are taking the knowledge maybe to another level and expanding it. Yeah.
Mm-hmm. Thank you so much for this insights. And I see a couple of questions coming in from the audience, especially targeting the main value from SimScale and also some Rimac related questions. But I think a follow-up question to this, Alex, would be other customers are also using SimScale as a solution. And they also struggle with this time to market transition. Is there anything maybe you would like to add, especially when it comes to a time to market transition using SimScale over any other classical CAE methods?
Yeah, so we see this very often. As mentioned, we really try to make a simulation accessible, but that relates heavily to this time to market question. So if you look at essentially what the challenges are for most product delivering processes or product design cycles, it's usually where people mention that it is about getting fast, kind of time to market is key. And being faster as competitors. I even found that on a presentation from Rimac Automobili, where it says essentially in our industry, if you're not first, you're last. So essentially the electric vehicle landscape is so competitive, it's so fast, and that also applies for most electronics heavy industries. So be this energy storage in general, be this consumer devices, it's many different areas. The design cycles are much smaller than other industries, and that means you just need to be fast. You need to be in the competition to have success. There's obviously other values that are listed here as well, but often it's really about this time to market, and kind of gives us again the chance to highlight again how the platform character of SimScale can get you to this. So we wanted to quickly show again kind of the realization and design phase of a product, which is listed here from concept to production during the different stages. And obviously the more important, the earlier you are in the process when you define how your product will look like, the better this is, and the more costly it becomes when you make design changes later on, maybe just because of a failed validation test and physical testing. That is obviously then a big problem. And this comes from essentially designers and engineers starting with a concept, starting with a design, optimizing already based on their experience and knowledge, which obviously is a key factor and can never be replaced. But the product often is already kind of matured at the moment where a simulation expert steps in, uses traditional simulation on his own desktop as kind of a service to the design department, comes back with some feedback, and potentially then another design cycle starts. So that is just, in a sense, late in the process and doesn't make the most use of it. You can see this highlighted here when essentially a simulation is mainly used. With SimScale, we really extend this from the beginning to the end. The designer might not have a detailed design ready. He might just have kind of a rough sketch of where he wants to place the components inside of an enclosure and already run a rough analysis and understand how this is working. And obviously, the simulation expert also gets involved much earlier because he can be the sparring partner of the designer, help him, give him some simulation template to support him, and later on, as the physical testing, serve as a additional validation step later on. But you're really expanding the usage of simulation to the whole design cycle, and that makes you much faster.
Thank you so much, Alex. And I think we can now move on to today's application, where we will show you how we actually optimize battery cooling system using cloud-based simulation.
Great. So let's have a look at this. As you can see here already, this is a battery pack that is simulated. We finally see the colorful pictures that everybody knows, mainly from demonstrating then also to your colleagues, right? But this has a real numerical value, and obviously the quality of results is important. So what results are we really interested in a battery pack? Usually that is the temperature inside, or the max temperature in the battery cells. It's usually the uniformity within the battery module, but potentially there might be more key figures or result fields. So kind of the question to Antonio, is there anything else where you're really interested in some key figures or result fields while running simulations?
So yeah, Alex, you were on right track. So the key figures or the key numbers here, which we are looking at, is first of all, what is the maximum temperature which can occur in the battery cells. Here we are thinking mostly about safety, so not breaching the temperature limits which are set for the cells. And second point is what is the thermal gradient across the battery module. You can see here the thermal gradient across the battery module is really important, because if we have high thermal gradients, the battery cells will behave differently, because the battery cell performance heavily depends on its temperature, and then you will have non-uniformity throughout the battery module. and this is not good because this will impact what is the aging of the battery pack and other performance values as well.
Great, really interesting. Thanks for already sharing this. We'll jump onto the next slide to show you how this battery pack looks, and maybe this is now a good moment to highlight. You saw the battery pack inside of the hypercar. You might also see that this is not exactly the same geometry. I guess it's clear, right? We mentioned how competitive the electric vehicles landscape is. So this battery pack that you can see here was designed by us and simulated together with Rimac Automobili in preparation of this webinar. Obviously, it's not the exact same technology, and it's not the exact same model, as we could never show this in a public environment. We hope this is understandable to everybody, but we can highlight obviously what this is about, right? And we can show how the simulation setup is generally done. We obviously can also demonstrate such an example to you if you want to give it a shot and have some looks at SimScale. You see here, this is kind of a standard battery pack. Couple of cells that were put together in this pattern, and we have it cooled. We will also see this later on with 2 aluminum cooling plates. At this point, it would be already interesting to ask Antoni as well. You know that there's different ways of how to do the cooling for a battery pack. That might be for a street scooter, just natural convection cooling kind of, or that might be forced air cooling with a fan or immersion cooling. In this case, we really have the liquid cooling indirect. Is there even a way around the liquid cooling for these high voltage battery packs that you are using for the hypercars, or is there different technologies that you're thinking about and that you can test and work with?
Yeah, so that's a really interesting question, and this is always an actual topic on the market. How do you cool the battery cells? As you already mentioned, it heavily depends on the requirement which the customer sets, which is closely connected to the battery cell design and to the performance values which the customer is targeting. So during the early design and development process, Rimac evaluates all options. So from natural cooling to liquid indirect cooling to liquid direct cooling, and evaluates what is the best design approach. Naturally, if you want to have a high performance battery pack and battery module, you need to go with the liquid cooling of the battery cells, be it indirect or direct even.
Great, thanks for sharing this. Let's look a bit more into this, right? How this liquid cooling then can look. For such a case, we give kind of some numbers at the beginning where you can see what this usually is about. Obviously, this is dependent on the use case and always a bit different. In our case, we have here this battery pack, 96 cells with 3 watt of power each. We have here a water glycol as a coolant liquid, right? This is not too much variation usually on that side with a certain inlet temperature. And our objective here is to increase the battery lifetime, really understand where the max temperatures appear and how high those are, and have ideally some uniform distribution. And we want to do so essentially by looking at a parameter study and figuring out what we can do and how we can improve essentially the cooling. This parameter study, we will look at 2 parameters that we want to vary. So that will be essentially the inlet flow velocity and the thermal conductivity of the electrical insulator. You can see those 2 values here on the right in this table. You might easily kind of now transform this idea of doing such a simulation with the concept that we kind of showed you in the beginning, right? So if you want to run such a kind of design of experiment or a study with many input parameters, multiple even combined, on SimScale, obviously, with the power of the cloud in the back, you can just run all of these simulations at the same time. So the time to result for you becomes essentially the time to result for one simulation for all of your simulations. In this case, this is obviously conjugate heat transfer. So we want to have all mechanisms of heat transfer, solid conduction and convection, that play a role in this setup. We run this in steady state and with laminar flow, and you can see what computation time we had for these 30 simulations that were ran. Good. Maybe here also a question to Antonio. How many iterations can you usually do if you're doing physical testing? So is that also where you can really vary the inlet velocity, or is that very dependent essentially on what to change, right? I guess for materials, it's maybe a bit more complex.
Yeah, so when you are doing physical testing, you are obviously limited by the geometry you have on the testing table. But yeah, flow velocity is something you can play with, and the inlet temperature control, etc. However, it is really difficult to vary some of other parameters which are maybe easily implemented in the simulation, such as thermal conductivity properties of materials or thickness of various insulation layers. So here you have some advantage in the virtual world.
Okay, that makes total sense. And could you maybe also give us a bit more, we see here again the battery pack with the cooling plates, kind of give us some understanding of the different components and which ones of those are essentially more or less given, right? And there's not much to optimize there, and what are really your key parameters that you can work with and where you can kind of, use all of your creativity and knowledge to get to a better result.
So here there are several aspects where the designer can make decisions which can improve the thermal performance of the pack. Mostly here the thermal interface between the battery cells and the cooling plate. So how are the interconnections which are carrying the current designed? How is the electrical insulation designed? What are the thermal properties of those layers? And also coming to aluminum cooling plate, usually the battery pack coolant temperature and flow rate are set with the vehicle level targets. However, the cooling plate design and the channel geometry is up to the designer to play with and to optimize it as much as possible. Basically, the sky is the limit in the number of iterations you are able to do. However, you must be able to evaluate when to stop, because after some points the gains will probably be marginal and there is no point in proceeding forward.
I see. And when we look at the simulation results, so here I think it's a bit small, but you can see there's for the different velocities, we get very different temperatures, max temperatures on these battery cells. Is the flow rate and kind of the coolant liquid, is that a parameter you can really play with, or is that something where kind of the whole car concept team comes into play, where you kind of need to find a trade-off, because likely the higher kind of the velocity and the cooler the cooling liquid, the better for you or your performance. So I guess this is kind of a trade-off you want to make with your colleagues, I guess, right?
Yeah, so usually with this analysis we are able to present them what kind of gains we can have if we increase the coolant velocity. However, this needs to be a vehicle level decision to see if this is really something which is worthwhile implementing into the design.
Great, interesting. Yeah, and once we're done, right? So obviously we ran here a study with 2 parameters. It could be more. Antonio mentioned many different key factors that you can count in. And you can obviously plot this in any way you're really interested in, but the key factor here, the highest battery temperature, can be then seen based on these decisions. And obviously you can go for whatever is economically and feasible for you to produce. So we really wanted to give you just an understanding or some insight of how such a simulation looks like, right? So that we kind of do not tell you about the benefits, but not show how then in reality this can be done. You can obviously join our offerings to do this yourself, or to get started together with us on trying such a thing. But that's how far we wanted to go with with our use case for today. And with that, I give back to Josef, please.
Yes, thank you so much to our guest speaker, firstly Antonio Radonic, and also Alex Fischer, for this very, very nice discussion, and also giving us a bit of insights on how Rimac is actually deploying a cloud native simulation inside their organization. So I can already see some questions coming in. So I think with that being said, let us move over to the Q&A session, and we'll now take your questions one by one. So feel free to ask Antonio or Alex some questions about the simulation, about cloud native simulation, or even Rimac, the use case itself. So I see a couple of questions coming in. question to both of you, Alex and Antonio, would be, from Rimac's experience, does SimScale also support conjugate heat transfer on electrical motors?
Thank you, Josef, for the question. As I work in the battery system department, I never really tried to run a conjugate heat transfer simulation on motor. However, I do not see a reason why it shouldn't be feasible. Yeah, from my perspective.
Interesting. From Rimac's experience, does SimScale also support conjugate heat transfer on other types of analyses? For example, are you using it apart from anything else than the battery system itself? But I mean, as you're a battery system engineer, Antonio, I think that's a quite broad question, right?
Yeah, so basically you do not have to be limited only to battery systems. Conjugate heat transfer can be used in any other application where you have a fluid in contact with some of the surface which you need to cool. So the application is really broad, from maybe cooling some electronics. Here Alex maybe has a greater experience than myself, but also to cooling inverters, motors, etc.
Okay, Alex, maybe you want to add your 2 cents here?
Yeah, so we also have these use cases, right? But as we are mainly focusing right now or centric around the thermal aspects, we definitely have more applications around the cooling aspect of the battery pack. But as we mentioned, we want to kind of become and be this bigger platform that really helps you in every design stage, also for each designer. What we do not yet cover, we are also really looking into it to add it to have the whole setup in place, essentially.
One question is coming in, which is asking, one of the heat transfers between cells is through the bus bar. How do you manage it inside of your simulation?
So obviously the bus bar model is included inside the simulation, and it is simulated, or it is covered with the simulation, because the current, the heat and the current can flow very easily through copper, as the thermal conductivity is very high, as well as electrical resistivity is really low in copper material.
I think that covers it very well. Thanks, Antonio. What types of cooling mechanisms can you simulate on the SimScale platform, and maybe even Rimac has deployed or used inside of their organization? I think that's a very interesting one. Either Antonio or Alex. Maybe Antonio, you can get started, and then Alex can add his 2 cents.
Yeah, so regarding the conjugate heat transfer, we mostly focused on liquid cooling. However, as I saw, it is feasible also to include air cooling, which is especially useful when simulating small electronics.
Yeah, maybe to add here, right, we mentioned this, that we cover with the conjugate heat transfer analysis all mechanisms of heat transfer, so conduction, convection, and radiation, thermal radiation. And we also mentioned the different ways how to cool down such a battery pack, right? So that we can do this via liquid cooling, immersion cooling, so direct or indirect via some cooling channel, or that we can do this with forced convection with air, or natural convection with air, or even with some phase change models in some way. And the only thing right now on SimScale that is not yet available is the phase change part. So everything else, so cooling via convection, liquid cooling is available. And also in case for your material, kind of for your pack or for your application that might differ from now a battery pack simulation, is if radiation is important, that's obviously possible to add as well, and have some surface radiation working here. We often see this, for example, with lighting fixtures where we have natural convection use cases, and we have a bigger heat sink with a kind of black colored heat sink, and then there's a bigger contribution, like 20% or so of the heat loss via thermal radiation. So that's also possible.
Excellent. Thanks, Antonio and Alex. I think we covered it quite extensively during the presentation, but still a very interesting question would be, can I run multiple battery simulations at the same time?
Yeah, so from our experience, you can set up a number of projects which can run in parallel. So you, for example, can prepare several geometries which you find interesting and simulate them in parallel, and then later just compare the results. So this feature is feasible in SimScale.
Yeah, so absolutely right. You can essentially you can just run one simulation and kind of scale this up and get the turnaround times for all the simulations you run down to one. Kind of more or less the sky is the limit here. Obviously, when you're running on SimScale, you have some computing quota. So it will be rather your decision how many different variations you want to run. It won't be ever a hardware or a licensing issue. But obviously, usually you'd rather spend more money testing this and saving time than saving here on the computing costs. At least that's our experience.
Excellent. Another question that's coming is, what other types of simulation besides thermal are possible? Maybe that one is for you, Alex.
So in general, there's many different physics possible, right? So if we are still focused on the electronics area, right, then it's additionally doing pure CFD analysis. So thinking more about pressure drops, or analysis like that. It's possible to do structural analysis. Is that it could be a vibration analysis that you want to do, or it might be a snap fit analysis, quasi-static nonlinear analysis, or it might be a transient nonlinear analysis of some contact modeling, so physical contact between two parts that essentially then touch or get into contact, so or drop tests, for example. All of this is possible. If we are expanding kind of further outside of electronics, there's obviously other options. You can do aerodynamic simulations. That's potentially also interesting if you're building cars like we see on this slide, right? That's possible, but also we're working with many companies in data center cooling that is adjacent to electronics, or in the whole AEC market where it's about urban wind comfort, wind loads, similar applications. So there's kind of trying to cover really in the CFD FEA area, if you see it from a method point of view, to cover as much as possible. So there's many additional opportunities. So if you're from a different industry, feel free kind of to check out our website. We have content for all of these different applications that you can have a look at and understand what's possible and if SimScale is a fit for you.
Great. Also a SimScale related question, how easy is it to change boundary conditions and material for different battery case studies? That one is for you, Alex.
So yeah, that's kind of easy, but it can be done in different ways. So if, for example, you want to, we saw that we did two different parameters here, right? And so if you want to, for example, do a study, you want to vary multiple parameters, let's say one material and the inlet condition, then you can obviously just copy your latest setup, change one value and start it again, right? That means you will spend some time creating maybe 5 to 10 different simulations. Shouldn't take too long compared to the simulation time, but you can also kind of automate this workflow with what we showed you in one of the previous slides, where we have a public API where you can just say, okay, I'm setting up one simulation, do this inside of the UI. That's just easy and fast, right? And I kind of take this as a template for my API use case, and then change this one value for the boundary condition and potentially multiple values for the material properties, and kind of start this as a script and run all of these simulations in parallel. And then also, if I want to, I can pull also the results via API. And if there's maybe just one value, or you want to process this in a special way, then you can also do that. So it's very easy to get from one design to simulating the next one, but you can also really automate it and make the most out of it.
That covers it quite well. Thanks, Alex. A Rimac related question for Antonio. From Rimac's experience, what are the limitations with SimScale's post-processor of results of the heat transfer cases for battery cooling? Did you see any downsides of the post-processor, Antonio?
So from our side, I can't remember anything that wasn't quite available. So the temperature gradient across the cell can be seen. The temperature gradient across the module, you can scale down the temperature scale. So from the post-processing side, I think everything is covered. Yeah.
Maybe one for Alex and also Antonio at the same time. How do you simulate the battery cell? Is it only a heat source?
Yeah, usually the modeling approach when you are modeling the battery cell is that the heat is evenly distributed across the cell volume. This is the usual approach which is taken.
Yeah, maybe I can try to add something here. So now, obviously, always dependent on your use case. It also depends often what's the physical testing environment you want to then compare against with simulation once you did the optimization. So we see different use cases here. We're also in contact and obviously discussing with partners about adding more advanced battery models, right? If that's required. But for the most part of it, we usually are looking rather at the bigger package level, and most of our customers really use this just as a power source and run a steady state simulation on it.
Excellent. Thank you so much, Antonio and Alex. We have also a couple of questions coming in regarding the data security of SimScale. And for that, you can feel free to reach out to me and I can send you some interesting articles and also blog posts from SimScale talking about data security. So that's no problem at all. One is asking if they can get the recording. Yes, this recording will be available on demand after this webinar. Apart from that, I don't see any more questions. I think with that being said, let's jump to the next slide. Just some kind of next steps. If you want to have a one-on-one demo, feel free to visit our website, simscale.com, or contact sales@simscale.com. And if you have any questions regarding battery or thermal simulations, my colleague Alex Fischer is so kind to help you out in your simulation journey. With that being said, I wait a couple of seconds, maybe some more questions are coming in, and then I think we can wrap it up. Also, a big thank you to Antonio and Alex again for this great presentation and discussion. It was very, very insightful. So I think there are no more questions coming in. Great. With that being said, thank you so much to everyone attending today's webinar. And as I already mentioned, this webinar will be available on demand. And for future webinars, feel free to visit simscale.com/webinars-workshops for future webinars like these ones from today. Again, big thank you to Antonio and Alex. It was a great webinar, and I hope to see you in a second part, hopefully soon in the future. Take care.